Hello everyone, I'm Jie Ren from University of California, Merced. Today I'm gonna present exploring non-volatility of non-volatile memory for high-performance computing under failures. This is a joint work with Kai Wu and my advisor Dr. Dong Li. Large-scale and HPC systems are the main computation platform for HPC workload, such as scientific applications. One of the main focus to maintain the system is the reliability. The metrics used here is mean time between failure. Theoretically, the system level mean time between failure equals to mean time between failure per node divided by the number of nodes. For the system that has 10,000 to 100,000 nodes, mean time between failure could be between 87 hours to 9 hours. This goes down when the system scales up. The traditional mechanism to handle failures in HPC system is checkpointing restart mechanism. The high level of the idea is that the application runs for a certain period of time, which is defined as checkpoint interval, and takes a checkpoint, which is to store the program states into a non-volatile storage, and runs another period of time and takes the checkpoint and go on. Sometimes, during a normal execution, there might be a fault occurring and affecting the application. The fault becomes an error to the application and later leads to a crash. For crashes, the checkpointing restart mechanism would stop the execution, roll back to the latest checkpoint, and restart from the stored programming states. A large portion of computation cycles will be used to handle application failures. The efficiency of the checkpointing restart system is measured as the sum of checkpoint intervals divided by the total time, including the checkpointing intervals, the total checkpoint overhead, and the total wasted computation overhead. People configure the checkpointing restart mechanism for the optimal checkpoint interval, which is a function of checkpoint overhead and the mean time between failure. So the longer mean time between failure, the longer checkpoint interval will be. For the system-level checkpoint, the checkpoint overhead is usually hardware dependent. Therefore, the question now becomes, can we do something to the mean time between failure, which leads to a longer optimal checkpoint interval and have a more efficient checkpointing restart system? Non-volatile memory is promising to provide a high-efficient, reliable HPC system. Intel recently released the Optane-DC persistent memory DIMM with a DRAM comparable performance, which can be used as the main memory for the system. Here we introduce how to persist data in non-volatile main memory. At the execution of the application, the data is placed into cache first. When there is a conflict of a cache line, the old data in that cache line will be evicted to non-volatile main memory. Relying on automatic cache eviction for persisting data do not incur any runtime overhead. However, data is inconsistent between cache and NVM. When a crash happens, the system loses data in cache. Another way to persist data in non-volatile main memory is to use low-level hardware primitives such as flash or fence instructions. After a data update, the flash and fence instructions can guarantee the consistency of data in cache and in non-volatile main memory. However, such low-level hardware primitives incurs large runtime overhead. Based on the features of non-volatile main memory, now we can rethink the checkpointing restart mechanism. Using flush and fence instructions to maintain data consistency in non-volatile main memory is expensive. It is natural to ask that, is it possible to recover data and resume application computation after the application crashes with the inconsistent data left in non-volatile main memory? If the recomputation result is not acceptable, we can recover the application from the last checkpoint. To study how application restart behaves with the inconsistent data left in non-volatile main memory, we perform an application recomputability study. We define application recomputability in terms of application outcome correctness. In particular, we claim an application recomputes successfully after a crash if the final application outcome remains correctly. To study application recomputability, we develop a pin-based crash simulator called NVCT. NVCT includes a simulated multi-level caches, main memory, and a random crash generator. To study the application restart behavior, 1, 2, 3 goes. To study how application restart behaves with the inconsistent data left in non-volatile main memory, we perform application recomputability study. We define the application recomputability in terms of application outcome correctness. In particular, we claim an application recomputes successfully after a crash if the final application outcomes remains correct. To study application recomputability, we develop a pin-based crash emulator called NVCT. NVCT includes a simulated multi-level coherent cache, main memory, a random crash generator, a set of APIs to configure crash test and application restart. NVCT is available online, and please check our previous paper for more details. Our application recomputability study contains a large amount of HPC applications, including benchmarks from NPB, Spec OpenMP, Rodinia, and the HPC application Lulash.
To ensure the statistic significance, we deploy thousands of crash tests for each application. The application recomputability equals to the number of successful recompute tests divided by the total number of tests. The figure shows application recomputability study with different applications.
We notice that some application shows very strong recomputability, such as BT and ST. Some applications such as IS, LU, and EP are the opposite. They cannot restart or have a segment fault. The take-away message here is that different applications have quite different recomputability. We further study the factors that impact application recomputability. We take application MG as an example. We first study if persist different data object in MG can helpful to improve the recomputability. We do not persist all data objects because it causes large performance overhead. We choose 3 data objects, iteration number IT, U, and R for study. We persist them at the end of each iteration of the main computation loop. By persisting data object U, the recomputability is improved to 63%. However, persisted IT and R, the recomputability is barely improved. The takeaway message is that persisting different data objects has different impact on application recomputability because of data access patterns such as data reuse pattern or read and write pattern. We further study the impact of where-to-persist data object on application recomputability. MG has 4 first-level inner loop, and they represent 4 execution phases. They all update data object U, so we persist U at the end of each execution phase, or we call it code region. Figure 2 shows the result. If we persist data object U at the end of each main computation loop, we have 63% of the recomputability. Persist U at code region 3, we have 21% improvement in recomputability, while persist it at the other code regions, we only have less than 7% improvement.
The takeaway message here is that the application shows different recomputability when persisting data object at different code regions.
To summarize the insights of the application recomputability study, first, different applications have different recomputability. Persisting all data objects throughout code region may not be useful and effective. Selectively persisting data object at some code region can be effectively bound the data errors caused by data inconsistency and leads to a better application recomputability, while paying less performance overhead. Based on above insights, we introduced EasyCrash, a framework to increase application recomputability on non-volatile main memory. As shown in this figure, EasyCrash persists the data object in some code region of the application. When the crash happens, EasyCrash restarts the application with the inconsistent data object in the non-volatile main memory, and does not need to go back to the latest checkpoint if the application outcome is correct. EasyCrash brings 2 benefits. The first benefit is that EasyCrash reduces the mean time between failures since EasyCrash can recompute the application with a high possibility use the inconsistent data object in non-volatile main memory. Second, EasyCrash reduces the wasted computation time and the checkpoint time in traditional checkpointing restart mechanism. The design challenge of EasyCrash is that how to automatically decide which data should be persisted and where to persist them. Here we introduce the details of how to select the data object, and please read our paper for more details on where to persist those data objects we selected. First, we select the candidates of data object to persist. The candidate's data object should not be a read-only data object, and it should survive the main computation loop. Otherwise, the data object can be read from non-volatile main memory after crash, or can be recomputed based on other data objects. Then we perform crash tests to collect the data inconsistent rate and application recomputability. Here, the data inconsistent rate evaluates the degree of data inconsistency. For example, a data object of 128 MB could have 16 MB inconsistent data, giving an inconsistent rate is 12.5%. We use Spearman rank correlation analysis to statistically quantify the correlation between inconsistent rate of data objects and application recomputability. With the selection of correlation coefficient, we select the data object to persist. We evaluate the effectiveness of EasyCrash on the latest Intel Optane platform, and the figure shows the result. EasyCrash significantly improves application recomputability. It enables to transform 47% of crashes that cannot correctly recompute into correct computation. We further evaluate the runtime overhead of EasyCrash. EasyCrash achieves high recomputability with no more than 3% of runtime overhead. For the comparison purpose, we show the overhead of persisting all candidate data objects at the end of each main computation loop, which is shown as the execution time without EasyCrash. This case costs 35% overhead on average, much larger than EasyCrash. To evaluate the system efficiency with and without EasyCrash, we use simulation and build the performance model for checkpointing restart system. As shown in equation 1, the system efficiency equals to the ratio of useful computation time to total simulation time, where the useful computation time is the sum of checkpoint intervals without crash happening. For the system without EasyCrash, the total time equals to the sum of computation time without crash happening and the restart overhead. Leveraging the mean time between failure, we can estimate the number of crash happens in a long simulation time.
For the system with EasyCrash,
The total time including three parts. The computation time without crash happens, the overhead of system restart from last checkpoint, and the overhead of EasyCrash successfully recompute the application from crashes. The number of crashes can be successfully recomputed by EasyCrash equals to the number of crashes times the EasyCrash recomputability. As the application recomputability increases, the overhead of the system restart from the last checkpoint decreases, which is helpful to increase the system efficiency. We assumed 100,000 nodes in system and the mean time between failure is 12 hours. We measure the efficiency of both without and with EasyCrash for different checkpoint overhead. We further scale at a large number of nodes and measure the efficiency of both with and without EasyCrash. For all cases, with EasyCrash has a higher efficiency than without EasyCrash. The takeaway message of those two figures are, as the checkpoint overhead increases, the performance benefit of EasyCrash increases. As the system scales up, the performance benefit of EasyCrash increases. To conclude, the emergence of non-volatile memory provides the opportunity for HPC to enable scalable scientific simulation and higher system efficiency. In this work, we propose EasyCrash, the framework to increase application recomputability on non-volatile main memory. EasyCrash relaxes the requirement on crash consistency, but with constraints for enabling the system efficiency. EasyCrash is able to transform 47% of crashes cannot be correctly recomputed into correct computation with less than 3% of runtime overhead. Based on the characteristic of error resilience instinct to HPC applications, EasyCrash has a great potential with a spectrum of HPC applications. Thank you for listening to my talk.